55 petabyte file system on Sequoia and ZFS. Brian Behlendorf.
So yeah, I'm going to talk about Sequoia's 55 petabyte Lustre+ZFS file system we're looking at deploying. I guess I'll try and go fast because we're running short of time. What I wanted to talk about was basically briefly why we've been following a path to get ZFS on Sequoia, and then a brief status update of where we're at, what we bought for hardware, our view on the current functionality and stability, and then some performance data from the system. We actually don't have data for the real system of Sequoia, but I do have some data from a smaller test system. We're unfortunately still integrating Sequoia now, so we don't quite have that yet. And then some open questions and then a summary. So why ZFS? It seems like there's always been a talk at the LUG about ZFS, right? It's always coming to Lustre real soon. Well, we're finally getting real soon, and the reason why has been we've been pursuing ZFS for Sequoia for scalability mainly. So ZFS buys us a lot of things. I don't want to go into like every feature of ZFS, although most of them are implemented at this point, but just touching on basically the drivers for this for Sequoia. So massive storage capacity, right? This is something that we saw coming with LDiskFS was going to be a problem. ZFS solves it for us. We get huge objects, huge pools, well beyond the 128 terabyte limit with LDiskFS today. Plus, we get some nice things for scalability, like a single OST on an OSS. And that's great when you're talking about deploying hundreds or thousands of OSSs. You don't want thousands or tens of thousands of OSTs, right? So cost is a big thing for us too. 55 petabytes of disk costs a little bit of money. So, you know, keeping that reasonable is good. ZFS helps us with that. At least the plan is in the long term, because we get a RAID LVM file system all in one, right? We can build on inexpensive disk, in theory just on JBODs, with no vendor lock-in. It's all open source, all good stuff. Data integrity, this is another big deal for Sequoia, right? We had a talk earlier about T10 diff. ZFS has built-in data integrity. That was kind of one of the core principles of the file system. That's almost paramount. Almost everything is built around data integrity in ZFS at the expense of other things. But anyway, so ZFS gets us with copy on write, which I think is often an undersold feature of ZFS. We get checksums on all metadata, all block data. This isn't true for LDiskFS, right? You can run a file system check, but only the metadata gets checked. Block data is never consulted, so you never know if you have bad block data. You usually rely on hardware RAID for that sort of thing. Checksums in ZFS are verified and read. We automatically get the damage repaired, all good stuff. We also get multiple copies of the metadata, which I think is also another resiliency feature that goes sometimes unnoticed with ZFS. So metadata is cheap, relatively, right? It's a small amount of data compared to your block data. So why not make a bunch of copies of it? ZFS does this for you. In fact, it even spreads them over different disks in the pool, so you can take quite a bit of damage to the pool and still be able to reconstruct the metadata, even if you do lose some of the block data. Ditto blocks are another feature for ZFS we may make use of in Lustre. Right now they're basically redundant metadata for actual block data in the file system. So if you've got a file and you want to have a couple copies of it, you can have ditto blocks for it. This is something we might make use of in Lustre because Lustre stores all of its metadata as normal files in ZFS. So it might make sense to have multiple copies of it. And then we get the normal ZFS redundancy, stripes, mirrors, RAID-Z. The other reasons are manageability. This one gets talked about a little bit less. But ZFS offers, from day one, it was designed with online everything, basically. So scrubbing is ZFS notions for checking the pool, reading back the data, verifying all the blocks are good. Resilvering is what they call a drive rebuild, basically. There's two flavors of this, actually, in ZFS. One is a full drive rebuild. If you pull out a drive, throw a new one in, whole drive gets rebuilt. The other one is if you just, some people call it a partial rebuild. You have a drive, you pop it out, it's offline for 10 minutes, 20 minutes, something like that. You put the same drive back. You don't want to incur the cost of a full rebuild for the drive. So ZFS is smart enough to actually only rebuild the bit that changed on the drive while it was offline, which is nice. Particularly when you're talking about tens of thousands of disks. Anything to minimize drive rebuilds is good. Pool expansion is another feature, config changes. There's other nice features like fast file system creation. I mean, this probably doesn't get talked about much either, but when you create a file system, right, it's a pretty rare thing to do, one would think, but we find ourselves doing it a lot at Livermore, it turns out. So being able to do that faster, that's a good thing. And we've got good utilities for all this. Oh, and by the way, in the current port, we get all these extra features that really weren't critical to us, but they come along with ZFS, which is nice. So we get snapshots, clones, which is what ZFS calls writable snapshots, compression you can turn on optionally, deduplication, a function called ZFS send receive, which lets you take a data set and send it from one node to another, basically, while preserving all the properties of the file system. That has some advantages for migrating file systems, possibly. Advanced caching in the form of a intent log or a read cache device, and then adaptive indiness and quotas are worth mentioning. But anyway, we get all of that in ZFS today on Linux. All of this is actually implemented today and has been in use for quite some time, at least through the POSIX layer for ZFS, if not through Lustre. So where are we today with Sequoia? So the storage hardware is here. It's on our floor. It's been assembled. Mark Stearman's going to give a talk later in the week more about the actual storage side of our hardware. We have the Lustre ZFS file system configured on the system. The file system is available to Sequoia users, but development is absolutely still underway. Right? So we've just started on the performance work, but there is a file system out there for to use. We've got a contract still with WhamCloud to finish the OSD work that Alex just talked about. This is scheduled to be completed in September 2012. We'll see. As Andreas mentioned earlier too, that this work should be available in 2.4. So you should be able to use ZFS in Lustre 2.4 if you want to. So very briefly, the Lustre Sequoia architecture. It's your standard Lustre architecture. It's just big, right? There's just a lot of it. So for our metadata servers, we've settled on pure ZFS config. So there's a pair of JBODs attached in a ZFS mirror. We've got 768 OSS nodes, each of those running a single OST. And that OST is 72 terabytes in size, and it's a ZFS stripe layered on top of RAID 6 hardware RAID. I'll talk more about that in a minute, but that's the basic hardware configuration. On Sequoia, we've got 1.5 million cores spread over 96,000 compute nodes, and those are all treed down into what the Blue Gene architecture calls I.O. nodes. So we've got 768 I.O. nodes. We've got 1.5 terabytes a second through the network switches between here, and we're aiming to get between 0.5 terabyte and 1 terabyte a second throughput on the system. So just a lot of everything. So what do we buy for hardware? Real quick, Mark's got slides on this later, but I have some performance numbers, so it's to put them in context, you need to know what hardware we have. So we've got NetApp E5400s we bought. They're a 64-bay enclosure. They've been around for a while now. We've populated them with 3 terabyte nearline SAS disks for 180 terabytes of raw capacity. They're IB attached, and they're attached to Apro Green Blades, which are pretty well equipped. The MDS side, like I said, just simple JBODs, 2 24-bay enclosures, populated with, in this case, 41 terabyte SSDs arranged in a ZFS mirror. These guys are just attached via SAS, and they're just plugged into a normal Supermicro node that's just got, I guess, 6 cores and 192 gig of RAM. So functionality, where are we at today in functionality? So I would say that the critical components are largely complete at this point. There's been great work by WhamCloud to get the OSD done. So the OSD API is, like I say, we've got work with them through September, but it's functional at this point. We've got one for LDiskFS, we've got one for ZFS, and all this other work came along with the Orion restructuring that Alex talked about. Andreas mentioned this earlier too, but I think it's worth pointing out again that some of the nice functionality you get with a ZFS backend now will be patchless servers. You can build ZFS and Lustre without patching your kernel. You can run on a stock RHEL 6.2 kernel if you want. That's big in my opinion. Under development still, quota work, change logs. We haven't yet integrated with the ZFS intent logs on the OSD code. for ZFS. That's going to be a fair bit of work, but I think it needs to be done. And we've got drive management issues still that need to be looked at. That's one of the reasons we're still using the hardware RAID, and we probably need some effort on this. So stability. Things are reasonably stable. We passed most of the Lustre test suite in our testing. It's stable under moderate test loads. We've observed issues under heavy testing on our test systems. We really pound on it. We've worked through a bunch of memory pressure issues that can cause out-of-memory events. We still have seen some Lustre and ZFS deadlocks. We fixed a bunch of them. There may be some left, but relatively few panics, actually. We tend to hit memory issues or deadlocks, at least historically, so far. We're obviously working to resolve all these issues. I mean, that's what we've been focusing on, is stability and functionality first. And of course, we'll fix any real-world issues that come out of Sequoia now that we have a file system there. So we think that by the time 2.4 rolls around, it'll be in pretty good shape. So performance. You'll notice earlier on I didn't mention performance as one of our goals for porting ZFS. This was never one of the focuses for porting ZFS. It was mainly a scalability and data integrity thing for us. That being said, performance has to be pretty good, right? It can't be amazingly bad. So I thought it would be good to take a moment to actually look at the current performance of the tree with a bunch of caveats here. One, we just started performance analysis. So these are some of the first numbers we've actually run in the code to see how it stacks up. Minimal tuning has been done to the ZFS side, and we expect there to be significant performance improvements. So don't consider this done. This is a work in progress. We are also mainly interested in some of the Sequoia workloads we expect to see. So that's lots of metadata and defensive I/O from our users, where we expect them to be dumping checkpoints from these 1.5 million cores to the file system, and that needs to work well. So on the metadata side, I thought it would be interesting to look at the two configurations for this JBOD you might set up. Right? You could either do 2 JBODs, which I've tried to draw here on the bottom, on the left, 4 drives each in this particular configuration. This was not on the actual Sequoia hardware. This is a smaller test setup we have. You could assemble those in a mirror using MD, put LDiskFS on top of it, export it. The other thing you could do is use ZFS, which is what we've opted to do here for Sequoia, and take those same drives, construct them in a ZFS mirror, and export a single MDT again. We've used SSDs, once again, for the better IOPS. We don't need that much capacity here, and this is all managed by Linux, basically. So how do we do for performance? So a test we use for this is called MD test. It does parallel creates, stats, unlinks. The test case here was 1 million files in a single directory, and we had 52 clients available, so we did it from 52 clients. So initially, things were pretty rough. We found some bugs in the code that caused problems right away. Right? So we had a problem with FID hashing we spent some time on, where we had a very poor hash distribution. It turns out this was fixed some time ago, and we only pulled it into the Orion branch after we identified the problem and found the fix upstream, so it's good it was fixed. We also had deadlocks early on with all this code, right? So we had ZFS Lustre VM integrations. Alex mentioned before that ZFS does its own caching with the ARC. There are still some issues to be worked out there, but we worked through those issues and got it working. I don't know if you can read the graph, but on top there is creates, and in the middle is unlinks, and the bottom is stats. So along with getting those bug fixes in, which were just bug fixes, right, we had some known work we needed to do for metadata. So a couple of those things were multiple object indexes, were a performance improvement that went into LDiskFS a while ago for the 2. I don't know which 2.x release they went in. But the idea is basically to store multiple of these object indexes due to mapping, right? For ZFS, they're implemented with a ZAP. ZAPs are known, it's an internal data structure for ZFS, but they're known to scale very well for capacity. You can put billions of entries in a ZAP and not have it degrade. But concurrent updates appear to be contended at the moment a little bit, so having more of them helps. And it's also possible that doing an insertion is going to cause a disk I/O, so that if you can do a couple of these in parallel, that's all good. System attributes were also a feature we know we needed to leverage because Lustre relies heavily on X adders. Exciters are very flexible in ZFS. You can have huge extended attributes, but by virtue of how they're implemented, they're a little bit slow. So we've used system attributes, which is a feature of ZFS that allows you to associate a bit of data very close to the D node on disk, so you don't have to do as many seeks. So this is a feature we've added, and it improves exciter performance. You can see in the graphs that, we went from probably a not very acceptable level of performance to a few thousand a second for creates and unlinks. Stats, on the other hand, seem to do very, very well. They did so well, I actually haven't looked into why they do so well yet, but 60,000 a second was respectable. So that's great and all, but how does this stack up to LDiskFS today, right? So this is the 2.2 branch with all the recent LDiskFS fixes, right? We've got the parallel directory improvements in here, the portal RPC code is in here, and it turns out that LDiskFS does quite a bit better than ZFS at the moment for creates and unlinks. So what's going on here? So it turns out we've just started looking at this, but there seems to still be some lock contention on the MDT, and that's limiting our creates and unlinks. But the LDiskFS data is interesting because it shows that clearly the higher level Lustre layers in our test rig are capable of doing better. So improvements to the ZFS layer should yield gains, right? We should get better performance improvements as we optimize that code. So on the server side, on the OSS side, I thought it'd be interesting to look at 3 configurations we might deploy for comparison purposes. So the 3 configurations I thought were interesting, starting on the left there, are what you would typically configure one of the net apps for, right? On the bottom there is one of these 60-bay enclosures configured with 8+2 parity. They're exported as 3 LUNs to the higher layer, and you would make, an OST on top of each of those LDiskFS file systems. The configuration in the middle one is actually what we settled on for Sequoia. This is the same configuration on the NetApp using their hardware RAID, exporting 3 LUNs to each node, and then in this case, we stripe ZFS on top of it and provide a single OST. This was basically done for drive management issues. At this point for Sequoia, we don't want to inherit the problem of managing 30,000, 40,000 drives, something on that order, right? For the moment, we'd prefer to let the RAID controller do that for us. That's just too many drives for us to manage, and we don't have the tools in place to do it today. However, on the right, you could export these as just JBODs and move all that drive management up to the node level and let ZFS use RAID Z2, eliminate the hardware RAID controllers entirely, all software RAID, and that's an interesting configuration to compare it to as well, because that's where we want to get to for these systems. So what do you see for write performance? So our test case here is a single file shared IOR running against just one of those OSS nodes. So this is a single OST running on a single node with 30 nearline SAS drives behind it. So if you look at the graph, it tops out there at about 1,600 megabytes a second for the node, and LDiskFS does pretty good. The graph is megabytes a second versus the number of client tasks concurrently writing to this server. LDiskFS does pretty good. That's not too surprising. It's been designed for this exact workload. It's had years of optimization work behind it, right? And ZFS comes in behind, but it's a new implementation. We haven't gone and optimized it yet. And there is additional overhead in the fact that we're still doing all these checksums, even if we've offloaded some of the RAID calculations to the server. So the interesting thing is where these lines go. So as you crank up the number of tasks per node, which is what we expect to do for our Sequoia workloads, right? We expect to be doing a lot of defensive I/O, and we've got 1.5 million cores, only 768 OSS nodes. So if you divide it out, that's about 2 million cores per node. There may be some level of aggregation going on there, but we're going to have lots of different concurrent streams writing to this server. As the graph I have here only goes up to 104 to 1, but you can see that basically, as you increase the number of tasks, LDiskFS performance drops off, but the ZFS performance stays consistent, right? This is actually exactly what we'd hoped for, and is one of the undersold reasons, I think, for using ZFS, is you can take, using copy on write, you can take this random workload and make it sequential and maintain that performance. So we actually do better than LDiskFS out at large task counts, which is where we expect to be. Interestingly enough, if you add the RAID Z2 line on here, we actually do pretty good. So not quite as good as running on top of the hardware RAID, but for higher task counts, we still do better than LDiskFS. And the limiting factor here is basically I/O size. When we're doing RAID Z2, ZFS has a very small internal block size, and we end up doing lots of small I/Os. So even though we get more IOPS here, we aren't quite able to hit those high numbers. So I don't want to dwell too much on the details of why, but it's do a pretty quick argument here. So why does LDiskFS degrade? So LDiskFS is divided into lots of statically allocated block groups, and basically it has less flexibility over which inodes and blocks must be updated. Right? They're all modify in place. And we've got the multi-block allocator with helps, but basically for lots of concurrent IOs, we degrade into random IO for LDiskFS. We end up spreading the blocks all over the place. So lots of seeks, it just slows down. The allocator they've used is desirable really for some workloads, small files, desktops, that kind of stuff. For concurrent IO, it just degrades. ZFS, on the other hand, only has 2 statically allocated regions on the disk it needs to update. There's labels at the beginning and the end of the disk that need to be updated with each transaction. But since it's copy on write, we're always writing new dnodes and new blocks, so we don't have the restrictions about having to update this or that particular sector. And we do these allocation decisions right as we're syncing out the pool. So all writes can be done sequentially. We can just take whatever's in our cache, sequentialize it, write it out in a big stream with big I/O. So that's why we see the performance we do and why it stabilizes there. There's obviously improvements that can be made. Increasing the I/O size here will help too, along with getting a better aggregation in the Linux elevator, but things do pretty well. So read performance. Read performance basically, as Andreas mentioned earlier, boils down to random I/O, right? For LDiskFS at the moment, that performs better than ZFS. Once again, due to the multi-block allocator. It's doing a much better job of keeping 1 meg IOs on disk, right? So when we read a 1 meg chunk for disk. ZFS is the maximum block size of 128K still. So we're doing random 128K IO in some cases, and that just doesn't perform as well. You can see it degrading there as the task count increases. Interestingly enough, though, the RAID Z2 numbers for the same configuration actually hold up better. And that's purely because we get more IOPS out of the drives when running them in a JBOD mode as opposed to running them on the hardware RAID. And that's enough to offset the degrading performance, it appears. So some things that can help this, I believe there's a talk later today on the network request scheduler. This would be a good thing for us. If we could actually get larger IOs, not just larger IOs to the server, but more predictable IOs so we could do better prefetching. The ZFS prefetching could be made aware to populate the cache more properly with things that are going to get cache hits. That would help. Larger IO sizes would help too, but that's where we're at today for performance. So we've got a couple open questions still regarding this work. One, how do we make use of the ZFS cache devices, right? We think they only make sense for OSSs, probably, because we've built our MDS out of SSDs, so adding more probably isn't going to help. Here we've got 2 cases that we're thinking about for the OSSs. One, the ZFS intent log, which is a ZIL, which is built for small synchronous writes. This could be helpful to speed up things like lock cancels or small synchronous IOs done to ZFS. That would be good. The other is the L2 ARC, which is another big read cache you can add with an SSD to ZFS. You could use it to cache the object indexes, which we found can grow quite large. Keeping them on an SSD would be very, very helpful, and having to get them from the primary store. You can also use them for a generic read cache. Some other things we were thinking about are compression. Is it worth turning on compression? We have no idea. We haven't used it on real user data yet to see if it actually, how much it helps and what the overhead is. I mentioned before ditto blocks, so we can redundant copies of the Lustre metadata to make it more resilient. And then things like snapshots are a feature we could take advantage for, like distributed snapshots in your file system. That's something that could be looked into. So in summary, I would say Lustre+ZFS right now is actually pretty usable, but there are trade-offs to be made still. I think ZFS wins for data integrity, scalability, manageability. Those are things we care a lot on the big system. But LDiskFS still does better in a lot of the performance categories, and that's where we need to focus some work. This work is expected in Lustre 2.4. If you want to get it, you can actually go to the website. It's listed there. We've got a page where you can download the latest packages. This is Livermore's version of the Orion branch. We're tracking WAM clouds and applying fixes as needed or things to integrate. We push them back into their tree as fast as we can. But that's actually what we're running on our system. And then the last thing about, I guess, is just let everyone know that along with this Lustre work came a full POSIX port of the ZFS file system for Linux. So there's a release candidate out there and a community of people behind it now. We've got packages for Ubuntu, Gentoo. You can build generic RPMs. I invite you to check out the website and the mailing lists. This was actually really valuable for the Lustre work because now we have lots of people running the bulk of the ZFS code on their desktops and servers and just stressing it, and it's holding up very, very well. So that's very encouraging. That's all I got.
Got a couple minutes for questions? Questions? Anyone?
Nothing.
You only get one question.
Just
I have a simple question. SSH to our cache is help for read, but what about write and modification of metadata of file system? Is plans to write something in this area?
So for reads, we've got the L2R cache, right? But you said that's just reads. For writes, ZFS offers the ZFS intent log, and that's pretty much what we're focusing on to get that integrated at some point in the future. Right now, the support's not quite there for that, but that would be for small synchronous writes to the file system to speed that up to a cache device. I would think for large I/O, at least on the OSTs, you still want to go to the primary pools. So I think you get that basically with ZFS. Oh, sorry. The question was, on the MDS in particular, you're going to be doing lots of small writes potentially, right? How do you improve that? I think the answer with ZFS is you're already moving all this data through the ARC cache for ZFS, so it's all getting cached out and then batched and written sequentially. So these writes should be aggregated, and since it's copy and write, they should go out sequentially in large blocks. So the normal ARC caching mechanisms for ZFS should help considerably with that.
What's the largest LDiskFS file system you created? Like I have 117 terabytes ZFS, but I don't know, does LDiskFS scale to that size?
I'm told it scales to 128 terabytes. I think the biggest one we've built at the moment is 16. Yeah.
Okay, let's give Brian a hand.
Catch me later.
Now we have Nikki.